Okay, so I want to talk now. Oh, look, happy green. Continuous random variables. And I'm going to turn to black because I can't take it. We are going to only focus on one type, because as you can imagine, they're smooth curves and there's an infinite amount of types, but we will only focus on one type, and that is the Gaussian distribution, or the normal distribution, or the bell-shaped curve. So typically it looks like this. It's representing a random variable x, a continuous random variable. The thing about the Gaussian distribution is that it has some very kind of fascinating properties. So I'm going to list those properties over here. Okay, one property is that the probability at any one point equals 0. What that means is, and I'm going to erase this in just a sec, is if you have just one point here at xi, you can't find the density or the distribution at one point, because there's no real area on the curve, because you're imagining everything sort of near it. So that's one thing, is that there's no probability associated at one value of the random variable. What we typically like to do is that if you take the probability between negative infinity, I don't want a comma, negative infinity to infinity, the total probability is equal to 1 or 100%. Okay, the other thing that happens is that the mean equals the median, and the mean is, what color shall we use? Purple. The mean is right here in the middle of the graph, mu. Okay, another property is that the probability of x being less than the mean is 50.5 or 50%, and the probability that x is bigger than the mean is also 50%. So that means that this, if you mark this as the halfway point, the probability over here is 50%, and the probability over here is 50%, as these two things say, and then the probability of the whole thing is equal to 1. So that's some properties sort of associated with the normal distribution. On the next page, I'm going to draw it again and draw all over it. So get used to seeing this drawing, as well as get used to drawing it yourself, because we're going to do it over and over and over again. So on the next page here, I'm going to continue the properties. Oh, I don't want purple, I want black. So here's my normal distribution. I better keep my purple thing down here. Okay. And we're going to do the properties continued. And the properties I'm going to talk about now are the empirical rule properties. And your book has talked about it before now, but I think it's best to talk about it now. So from the previous slide, the mean is in the middle. Okay, then you can break up the continuous random variable, this is x, into some other parts. So this is mu plus 1 standard deviation, and this is mu minus 1 standard deviation. Then you can go out and go mu plus 2 standard deviations, and then mu minus 2 standard deviations. And then furthermore, you can go one more out to mu plus 3 standard deviations, and then mu minus 3 standard deviations. And we don't tend to go more than 3 standard deviations away because of what this empirical rule says. And it says that the probability in between the first standard deviations on either side of the mean, that the probability is 50%. I can't believe I just said that out loud. It's not 50%. It is 68%. So the empirical rule kind of at that point says that the probability that you are mu plus or minus a standard deviation away. Let me do better notation. I don't like that notation. It's not real clear what I want to say. It says that the probability of being less than a standard deviation on either side, good lordy, on being either side of the mean equals 0.68. Okay? It furthermore says that if you go in between 2 standard deviations of the mean, at that point you get 95%. Okay, so the second part of the empirical rule is, I'm going to write it down here just because I have more room, is that the probability, if you have 2 standard deviations on the left side of the mean to 2 standard deviations on the right side of the mean, that equals 0.95. And what you can see graphically is that, yeah, there is a lot of kind of gunk in between here. It's where the majority of the area under the curve lies. And the third one says that if you're within 3 standard deviations of the mean, that you get pretty much everything, or 99.7%. So the probability that you're 3 standard deviations on the left side to 3 standard deviations on the right side is 0.997. And so what that means is that the probability kind of out here in the tails, where I'm coloring in yellow, the probability of being out there, the probability of being bigger than the mean plus 3 standard deviations, well, that's really almost equal to 0. It's not equal to 0, but it's almost equal to 0. So what we're going to do is we're going to work with these random variables, because what you'll see is a lot of random variables in the natural world follow this kind of shape of distribution. Like most people's heights, if you put a bunch of nursing students in a room and they all take the blood pressure of one person, all those blood pressures will follow a normal curve, meaning some people will get a really high blood pressure, very few people will get a very low blood pressure, and for the most part, most people are going to get the blood pressure sort of right there in the middle where the blood pressure really is supposed to be. So what I want to do is some examples here using this normal distribution and the empirical rule, and then what if you can't use the empirical rule, how do you find probabilities inside the distribution? So that's what I'm going to focus on next, and I'm going to really do it by an example. Okay, so my example here is going to be talking about the age of undergrad students at UNM. Okay, and you can imagine, how old are undergrad students at UNM? So X is the random variable, and it represents the age, and x is normally distributed with mean equal to 23 and the standard deviation sigma equal to 2. And typically in all problems that we deal with the normal distribution is those are always given to you. You don't have enough mathematical background to find those on your own, nor do we expect you to do that. So that's always given to you. You don't have to be concerned with how those come about. It's by taking sample after sample after sample after sample of undergrad students at UNM and finding what their average age is, and then that can be assumed to be the population average age at UNM. So from that information in this problem, I know I can draw my little picture here, which get used to drawing these. There's my little picture of the distribution. My mean here is 23, and if I go up and kind of mark out this standard deviation, I can go to 25, 27, and 29. So I'm adding the standard deviations. This is the same as mu plus 1 sigma, mu plus 2 sigma, u plus 3 sigma, and then vice versa. I'm going to take it away on this side. I'm going to take away 2 because that's one standard deviation. I'm going to take away 2 because that's another standard deviation, and then I'm going to take another. Okay? So what this says is that if we use the empirical rule, I can say that the probability of a student being between 17 and 29 is 99.7%. And you can think about it. Think about UNM and look at the undergraduates. Are the undergraduates, do their age ranges really go between 17 and 29? Yes, you almost get everybody there, but there's always that sort of, outlier student who's 35 in your class, or the 15-year-old over here on this side who takes calculus, and they're a very small percentage of the population of undergraduate students at UNM. If you included the graduate school, everything might shift up because graduate students tend to be a little older than undergraduate students. Okay, another example of using the empirical rule is what is the probability that X is bigger than 23, that the age of students at UNM is bigger than 23. Will you mark 23 here on your graph here in blue? And you can see that what I'm looking for is this stuff right here, and that is 0.50, right? Half of the students based on my distribution function here. Okay, I'm going to erase that so I can mark it up a whole bunch. You will basically mark up these graphs over and over and over again, so just redrawing them might be easier, but I have this fancy tool so I can just erase, okay? What if I want to do, this is a harder one, the probability that people are between the ages of 21 and 27. Okay, well, that's a little bit different because we're going to have to break it up into its separate pieces, right? So the first one, I'm going to kind of mark it here. Here's 21 to 27, and I really want how much is in this part of it. And so what I do know is that, I'm going to kind of take away that coloring there, is that I can use my empirical rule, and in between 21 and 23, sort of this section in here, I know that within that section, it's 1/2 of 0.68, or 1/2 of 68%. If you are saying like, what? Where'd that come from? Go back to the previous slide, and I show you that right here, it's the 68% that's sort of covered in yellow, but it's because I'm halving. I'm one standard deviation below and one standard deviation above, so I'm just taking this half right here, which is 1/2 of 68. Okay, so then I kind of got to go in between the next parts, right? And so I'm sort of dealing in here now, right? And this, we know, is half of 0.95, right? Because 95 would be, if you go back to the previous slide, 95 is the green amount, and we only want this half right here. So we're going to take half of 95. So we go here and we compute each of those values. Half of 68 is 0.34. So we know over here it's going to be 0.34 plus, and then we have to go to half of 95. And what's half of 95? I'm waiting on you. Get half of 95. You got it? Okay, it's 47.5 or 0.475. So I add to it 0.475. I add those together. And I get 0.815 or 81.5%. And so you could say from this example that 81.5% of UNM undergrad population is between 21 and 27. And that's probably, who'd want to know that? I don't know, maybe like club owners in Albuquerque who want these age group of people to come into their establishments on Friday night. I don't know, but this is how we use the empirical rule to calculate different probabilities. Now, what if I give you a question sort of using the same example of UNM, remember, and I say, well, what's the probability? I'm using a bracket here, it doesn't matter. What's the probability that I'm between 22 and 24? What if I want to know that? So I kind of go back to my original distribution that I just had. The mean is 23, and this, right, it's where it had mu equal 23 and sigma equal 2. So I go here and I say 25, right? It's the exact same distribution that I was just dealing with. 21, 19, 17. Okay, and I see that I'm between 22 and 24. So I'm right here to right here. And I want to know what that is. In no way can you use, not B, the empirical rule only can be used within the standard deviation. So what you can't do is you cannot in any way say that, well, because this is half, right, between the mean here, that's 0.17. Somehow half of the overall 34%. Do not do that. That is wrong. This is wrong. It may be close to that, but it's wrong. And it's because the curve is not triangular. The curve is smooth and rounded. And so you cannot use the empirical rule if you are outside any of the normal standard deviation. So what you have to do is you have to use, you must, whoa, that's not how you spell use. You must use the z-tables in you have to use the tables in Appendix A of your book. but we have to do one thing before we can do that. So do you like red? I'm not liking red right now. Let's take red out and go to black. Okay. The tables in Appendix A of your book use what we call the standard normal curve. Okay, the standard normal curve looks just like the normal curve, except that the mean is 0 and the standard deviations are 1. So it's very different. It's where the mean is 0 and sigma is 1. The empirical rule still applies, meaning the 68, 95, 99.7 rules still apply. What this does is this allows us to transfer any normally distributed random variable into a standard normal one. And the formula, the formula to transfer is z equals x minus mu over sigma. So the random variable is z on this axis. These are called z-scores. And your book has had you compute some z-scores previous to now, but this is why we need them. We standardize them to make them work. So I want to prove to you that this works, okay? So I'm going to proof using an example, which is really not a mathematical proof. It's an example, but hopefully you believe me that it works every single time and therefore can be thought of like a proof, okay? So let's do the UNN random variable of age, okay? And that one was x. And then down here we're going to have the standardized or the standard, could I say that again? The standard random variable of age. Okay, so this one's going to be called z. Okay, so here's the first one. And we know how, right, we've done this enough now. So we know the mean is 23, and then we have 25, and then we have 27, and then we have 29, and then we have 21, then we have 19, then we have 17. Okay, and what I'm going to do is I'm going to turn that into the standard normal curve by completing a z-score for each one. Okay, so it's the exact same graph. Imagine those look exactly the same. And what I'm going to do is I'm going to turn 23 using the z-score. So I'm going to take x, which is 23. I'm going to subtract off the mean, which is 23, and I'm going to divide by 2. I'm using this formula over here. Well, 23 minus 23 is 0. 0 over 2 is 0. Okay, then I'm going to do it for one standard deviation. So this one's going to be 25. I'm going to subtract off the mean, 23, and divide by 2. That's 2 over 2, or 1. So 25 just became 1. 27, running out of room here, is 27 minus 23. over 2. And 27 minus 23 is 4. 4 divided by 2 is 2. So I just turned 27 into 2. And then I can do it for 29 out here, where 29 minus 23 over 2, that's 6 over 2, which is 3. So I just turned 29 to be 3. I turned 27 to be 2, and I turned 25 to be 1, and then I turned the mean to be 0. I can do that on the same way over here, right? That this is transferring to -1. You can do the math and look at that yourself, that this is transferring to be -2, and that this is transferring to be -3, and the empirical rule still applies. So this is just proof to show you that this equation to get the z-scores does take a continuous normally distributed random variable and turns it into the standard normal. Okay, so what this does is it allows us to compute probabilities inside there. So what I want to do is I want to show you how the tables work. So what I'm going to do is I'm going to move right now into your textbook. So I just pulled up on Pearson your Appendix A textbook. And what you can see is there's the picture that we've been dealing with all along, and that it gives you sort of probability shades. If you go, let me switch to my mouse here. Okay. If you go down, what this is this is all, I need to erase that real quick. It shows all the probabilities kind of calculated between negative infinity all the way to 0. And you can see that if z is at -0.5, that means that if I'm in z -0.5, -5, not -0.5, that's way over here. And the probability of being less than that is really tiny. Whereas if I go to 0, you can see down here at the bottom, what that means is I'm at the z-score of 0, and it's telling me the probability is a half, which you knew that from the empirical rule. Okay, so it's no different than the empirical rule of what you kind of were seeing beforehand. It's just the way it's been done. And what this does is it allows us to go outside of the empirical rule to calculate all kinds of probabilities. This number right here, if I want, what if my z happens to equal -2.46. Well, -2.46 is, here's -2.46 is this number right here. And what that means is, in my picture, is if I'm here, and here's 0, here's -2.46, I'm calculating that probability, and that probability is the 0.0069. The probability of z being smaller than -2.46 equals 0.0069. Vice versa, you can use the idea that it's symmetric, that if you want the probability that z is bigger than -2.46, you will do 1 minus 0.0069, because you're taking the whole probability distribution and subtracting off the tail of it that's shaded. So you're finding, in this case, hopefully this changes colors, in this one you're finding all of this probability in this example, and that is equal to 1 minus 0.0069, or a lot of probability, 0.9931, or 99.31%. So that's kind of how we use this table to calculate the probabilities, and you could see that what this means, this value right here, this negative 2.46, what that means is you are 2.46 standard deviations to the left of the mean. That's what it means. Okay, and it just so happens that we're in the standard normal curve, so the mean is actually 0. Okay, I want to erase this and talk about what other kinds of things are going on with all these tables. Okay, you can see here that there's the end of A1. If you go to the next page, it gives you the z-scores if z is a positive number. So see, z is a positive number. Again, it calculates just the same. Here are all the probabilities. You can see these numbers are bigger because of where z is on the positive side of 0. This little white part here is the same as the shaded part on this one. So it's just like the opposite tables, and you can use them for sort of how you want to, what's easiest for you to do these problems. Okay, so I'm going to use this table to finish this example that I'm working on. Okay, so let's remember where I kind of was. I want this problem right here. Okay, so I'm going to do it on the next page. Is at this UNM undergraduate aids, I want to calculate this. Okay, so I'm going to go over here. I gotta get a new piece of paper. And I gotta get my pen. So I want the probability that I am between 22 and 24. It doesn't matter if these have equal to signs below or not, because it's a continuous random variable, so it's the same as saying this. Just a side note here. It's really no different. Okay? So I need to get this, right? This is representing this graph where the mean is 23. Okay, I need to put this in the standard normal curve. I need to put it in this one. Okay, and the way I do that is I just convert it, use a z-score. So I use the z transformation that I taught you just a second ago, which is z equals x minus mu over sigma. Okay, so I do that. I do the probability that I have 22. That's my x-score. I subtract the mean, which is 23, and I divide by the standard deviation, which is 2. Okay, then I'm going to do it for 24 as well. So I do 24 minus 23 all over 2, and I get the probability that I get negative 1 over 2 is x to 1 over 2. If I transfer it to decimals, I get the probability that I'm between negative 0.5 and 0.5. Okay, we knew that. We knew that it was half a standard deviation away because of where 22 and 24 were compared to 23. So what this does is it just took the number 24 and, whoa, how about the number 22 to 24, right? That's what we're finding here. And we just transferred that down to negative 0.5 to 0.5. And we're going to find this. It's important that you look at the picture that we're finding. And so what we're going to do is we're going to use the tables. Okay, so we got to go to the table and look, okay? So I go to the table, and you can see I'm going to actually use the other table, and I'll show you why. Because I want to find, right, take the picture that I just had. I want to go from 0.5, negative 0.5 to 0.5 from the previous picture, and I'm finding this probability, right? So I could do a couple things. I could look there, I could find the probability from the table here, add it to that, and subtract from 1. That's one way to do it. Or I could go to the next page. Let's see if it lines up right. Let's do it. Let me erase here. Or I could go here and go to, here's my 0.5, and here's my negative 0.5, and then since I'm finding this, I'm basically going to find the whole thing, right? I'm going to get this whole thing, and either way, it's going to kind of be a lot of work to do it, okay? So let's just use this one, okay? So let's find the probability that x is less than 0.5. So that's kind of all of this probability, okay? So we're going to use the table to do that. So I go to z is 0.5 right here, and the probability that I'm less than 0.5 is 0.6915. Okay, so that's the whole thing. Then what I'm going to do is I'm going to use the previous table to take away, I'm going to take away this little part, okay? So I go to the previous table, and I want to find this part right here at negative 0.5. So I go down in my table to negative 0.5, which is down at the bottom. There, that one's lined up on it. And negative 0.5 is 0.3085. So the probability that x is smaller than negative 0.5 is 0.3085. And what I want you to notice is if you add these two numbers together, you get 1, because then we're filling up the whole normal distribution. Okay, so that's kind of what we're doing. So if we go back to our lecture here, we know that this probability here is 0.6915, and we know that this little probability here is 0.3085. Therefore, this probability, if we just get what's in the middle, is 0.6915 minus 0.3085, and that happens to equal, do your calculation, 0.383, or 38.3%. So that's the answer to the problem. What's the probability of students, or the proportion of students between 22 and 24 at UNM undergraduate students? And that is 38.3% of them are between those two. And you can see that now we can answer any kind of probability question that we need to, as long as we use the z-scores and the fact that we understand how the tables work in the normal distribution. The next lecture will just be computing a whole bunch of probabilities for an example. So I'm going to stop this one now so that we can work on that at the next one.